Hello, my name is Jack Fitton, and for my extra credit dynamics problem, I'm going to be assessing a seesaw because over spring break we're at the beach and there was a little playground we passed by when we walked to the beach, and I saw it and I knew it'd be perfect for analyzing in terms of forces and kinetics. So if we were thinking hypothetically of an example of two kids on each side of the seesaw trying to balance the seesaw, we could first start by drawing an FBD and a KD for that seesaw. So if we had, let's say, a bar, and it's balanced on this fulcrum with, let's say one kid is heavier than the other. So we have one kid right here about 2 meters away and one kid about right at the very end that's 3 meters away. And so we can say this kid is A and this is kid B. So for this FBD, we have the mg of person A and mg of person B. But we also have a normal force at the center of the ground pushing back up on the seesaw from the two kids' weights. So this is a complete FBD of the seesaw. Also though, you have to account for the moment. We don't necessarily know hypothetically which side it's going to be rotating on because it can be balanced. So we can just draw a general moment about, and we'll put this center fulcrum at point C. So this is the complete diagram with the forces in the y direction and also the moment, which we hopefully will be setting equal to 0 to find a balanced seesaw. And then we're also going to have to set this equal to a kinetics diagram. I'll just redraw it real quick. So this kinetics then is also going to have a potential acceleration in the y direction and a potential acceleration in the x direction, and also an inertial rotation of about point C. So the moment of inertia times the angular velocity. However, we know that my is going to be equal to 0 because the system itself as a whole is not going to be moving in the y direction. So we can set that equal to 0. We can also determine that this will also not be moving in the x direction. It's a stable seesaw. But there is going to be a moment of inertia, which we can discuss in terms of distances away from the center. So back to the FBD, we're just going to set up these force equations. So sum of forces in the x would be 0 and equals 0, check, because there's no x directional forces and there's no acceleration in the x direction. Sum of forces in the y, we have a normal force pointing up, and we can also define the direction of positive directions for both y and x. So we know that n is then positive in this case, and then minus these two kids' weights, which can be set equal to 0 because the acceleration is 0 in the y direction. And then we can do sum of moments as well. And basically we're going to be able to somehow find the masses of both these kids in order to balance the overall seesaw. So the moments are going to be the force of that, the force times the distance away from the point that we are finding the moments about, which is C. So first we can do n, which has a distance of 0. So that goes to 0. And then we can do, and technically these are going to be opposite signs because one is counterclockwise, this one's person B is clockwise, and person A is counterclockwise. So we're going to assume also counterclockwise is positive in this case. So we're going to do plus MAG times 2, because distance 2 away from point C, minus MBG times 3, which will be set equal to 0. Because in this case, this will be 0. The moment of inertia times angular velocity, because we're trying to balance the beam. In this case, there'll be no rotation in either. So that can be set equal to 0. So now we know we have 2 equations and 3 variables. But if you look at it, I guess I need to define one of the masses. So MB is equal to 3, let's say, mass of 3 kilograms, which is a very lightweighted child. So in this case, then we can just look at MA G times 2 minus 3 times G times 3 equals 0. We can do simple MA equals 9 times 9.8 over 2 times 9.8. These cancel, which equals 9 over 2, which equals 4.5 kilograms. So as you can see, if you look and trying to balance that seesaw, you can find the mass of the other kid in order to keep that seesaw balanced. But also I'd like to talk about if we were to actually have the seesaw rotating in this problem, then there would be a moment of inertia. And so this moment of inertia you'd have to, in order to find that moment of inertia, you'd have to add up the 3 different masses that are acting on the seesaw. We would have the moment of inertia of the beam, so I, B. Well, I guess we'll call it I, C, since we already have a person labeled B. So we'd have to do the moment of inertia of the beam plus the moment of inertia of child A plus the moment of inertia of child B. And so in this case, these 2 kids would be treated as a point at a distance away from C, while the beam would be treated as a moment of inertia of a beam rotating about point C. And then you would just add those 3 moments of inertias up to find that moment of inertia. But I'd also like to point out that based on where these kids are distance away from this beam, or the center of fulcrum, the moment of inertia will change. So if these kids were closer, the moment of inertia would decrease and therefore would move faster, because in that case, since IZC is smaller, the angular velocity would have to be greater. And that's also a general analysis that you can make on these different types of systems based on the different moment of inertias that you're going to be calculating. So this is my analysis of the seesaw, and I hope you enjoyed.